Hello there. The flow of execution of our programs can take many paths and result in different states that our program can find itself in. Some paths are obvious to us and our programs arrive at expected states, but sometimes they don't arrive at expected states and we have unexpected behavior. The program finds itself in a place where it doesn't know how to behave, and that's why we have runtime exceptions. It's an exceptional state. In principle, our programs manipulate the data that is composed of the primitives, such as numbers or strings, which is a layer on top of raw bits. And obviously this layer of abstraction is not enough these days, and our programs handle more and more complex domains. However, there are clever tricks to model our domain in a better way and limit the amount of paths that our program can take, and as a bonus on top, make sure that the compiler can verify that we handled all of the possible scenarios that we wanted to handle. One of these tricks is a sum type, also known as a coproduct, also known as a disjoint or discriminated union, depending on whether you consider this from the type theory, set theory, or category theory point of view. As we all know, TypeScript also features the discriminated unions, and in this video I want to explore them more deeply. In type theory, we have this thing called tagged union. They're also known as discriminated union, or variance, or sum type. They are mostly known in functional programming languages such as Haskell or ML, but this concept can also be found in more modern languages such as Rust. As a main advantage of the tagged union is that the compiler can check whether all the cases are handled. Yes, the tagged union occupies some space, but I would argue that that's negligible. The tagged union can also be used for representing the optional data or exception handling. The canonical example of a tagged union is a tree, which is a data type that is defined as either leaf or node, and node contains an integer value and two links to two branches. Another good example of a tagged union is a result type that helps to represent a computation that may fail. For Haskell, that would be either A or B, which is constructed as left A or right B. Essentially, we can call this constructor on A and get the either AB, or we can call this constructor right on B and get either AB. Alright, we looked at the discriminated union from the type theory perspective, but broadly speaking, in TypeScript, types represent sets. So let's have a look at the discriminated union from the set theory perspective. Here we are, and in this article on disjoint unions, there is a diagram that depicts how to build a new set out of these two to create our disjoint union, which is a third set. As you can see, there are two sets, A and B, with similar items. And in the resultant set, the items are labeled by the set from where they come from. Otherwise, we wouldn't be able to tell whether this pentagon is from A or B. But in programming, if our types represent sets, how do we label them? Well, coming back to our tree example, leaf and node will be these labels. Left and right will act as labels for A and B. Technically, A could be a number and B could be a number, and without these labels, we wouldn't be able to tell the difference. Alright, this article invites us to look at this situation from the category theory point of view. And in category theory, the disjoint union is defined as a coproduct in the category of sets. Let's have a look. But before we continue, I just want to mention that in category theory, we don't talk about sets or other mathematical objects. We talk about the objects in a category. So X, Y, Z could be sets or anything else, and this F and G could be all possible functions between these sets. But we represent all these functions, all these possible functions as one arrow and call it a morphism. Another important point to mention is that these two morphisms, F and G, can be composed to get a new morphism that goes from X to Z. In other words, if X, Y, and Z are a string, number, and boolean, we could have functions from string to number, from number to boolean, and of course we can compose this two and get a new function that takes us straight from string to boolean. So broadly speaking, we can think of TypeScript's type system as a category where objects are types and morphisms are all possible functions between these types. But if in category theory we don't talk about sets and their elements and their functions on them, how do we prove that the properties of the underlying mathematical objects are still respected? Well, we make the diagram commute with the help of additional morphisms and additional objects. And if diagram commutes, this means that we can compose the morphisms in this way. So that means that we can first go from X to Y, from Y to Z, or by composing these two morphisms, we can get from X to Z. In other words, regardless of what kind of code we write, if our input is X, we should be able to get to Z. And if I manage to spark your interest toward the category theory, I highly recommend Bartosz Milewski's channel, where he explains all the details and intricacies of category theory for programmers. The link will be below. Alright, let's get practical and write some code. Well, I wrote some code beforehand, and here we've got two types, USD and Euro, and the union of these two types. And so the resultant set of this union will look like this. It will contain the elements of all the USDs plus the elements of all the euros. There are also two helper functions that just wrap a number into the corresponding type. And there are two functions that take us from our x1s or x2 to the union. Technically speaking, these two functions are our labels. They take two numbers and attach labels to them. So they act as those constructors that we saw before. But because of the limitation of the language, I just wanted to make it very clear what's going on here. We also have our type y over here, and it's just a made-up type. It doesn't really matter what kind of type it is. Two functions f1 and f2 that take us from our x1 and x2 or USD or euro to y, and our function f that takes us from currency to y. And as you can see in our scenario, we have to handle two cases for USD or for euros, otherwise we don't know which one was used to construct the value of type currency. You can imagine that there could be different business rules based on whether we've got euro currency or USD, and this code represents these two branches in our business logic. And so finally we have all the pieces of the puzzle to make sure that our diagram commutes in our TypeScript. And so if we compose f after I1, that would be the same as just taking f1, and if we compose f after I2, that would be the same as just taking f2. In all four cases we arrive to y. And so the simple example represents how we can lift our code from dealing with just primitives such as number to dealing with a higher level concepts from our domain, such as currencies and specific currencies, and how we can make sure that if we add another currency, the compiler will tell us that we have to handle this case as well. So hopefully you can see how the sum types can be useful to create robust APIs. On this note, I hope this video was useful and helpful and fun, and I'll see you in the next one. See ya.